Familiar to us all as it speeds along the world's trunk routes and motorways, the diesel truck is an essential part of our transport system. That the diesel engine is equally vital elsewhere is perhaps less well known. It has in fact been developed to meet a vast range of applications. In the process, it has been designed in a huge variety of types and sizes, until it has become the most versatile power source we possess. Most numerous are the small, high-speed diesel engines used in road vehicles. Like gasoline engines, the cylinders may be in a straight line or in a V configuration with two banks of cylinders sharing a common crankshaft. There may be anything from 4 to 12 cylinders, and the engines generally work on a 4-stroke cycle. Induction, compression, power, exhaust. But there is one fundamental difference from the gasoline engine. The inlet valve admits air only. This air is compressed to such an extent that it becomes very hot. And when the fuel is sprayed in, combustion occurs spontaneously. No spark is needed for ignition. This elimination of the spark and associated electrical system is one reason for the diesel's popularity: simplicity of operation and increased reliability. The higher temperatures involved and the high compression ratios used also mean that the construction of the engine has to be pretty rugged. This too can prove useful. Then there is the fuel. Diesel fuel is neither highly inflammable nor particularly volatile. At sea especially, this safety factor is a vital one. Most important of all, however, is the engine's thermal efficiency. The diesel converts almost 40% of the fuel's energy into useful power, compared to about 25% for the gasoline engine. In fact, the diesel is the most efficient of all heat engines now in widespread use. From the small engines used in cars to the larger ones used elsewhere, it is always economical to operate. As a result of its basic efficiency, engineers have used and adapted the principle of the diesel in various ways. The high-speed engine, as we have seen, burns relatively small amounts of mixture very often in a given time. Up to 2,500 times a minute, for instance. It needs a refined fuel. In other engines, the volumes burnt each time are far greater, but it happens much less frequently, only 70 or 80 times a minute, and the fuel can be of lower quality. The small engines need their high running speeds to produce a worthwhile power output, but high speeds raise the problem of engine breathing. The exhaust gases must be replaced by new air in a fraction of a second. It is to achieve this that most designers have opted for the 4-stroke cycle. This makes it easier to discharge the spent gases effectively and to draw in clean air. And in the larger and more powerful vehicle engines, 4 valves may be used to improve the airflow even further. For road transport vehicles, there's a demand for engines which give more power without themselves being any heavier. One way of achieving this is to fit the engine with a turbocharger. A small turbine is driven by the engine's exhaust gases at speeds of up to 120,000 revolutions per minute. This is coupled to an impeller drawing in fresh air. So the air going into the cylinder is already compressed, and a greater weight can be packed in. Each combustion burns more air-fuel mixture and thus produces more energy. On a multi-cylinder engine, the turbocharger is fed by and delivers to all the cylinders in turn. Turbochargers increase engine output by about 25%, and they're widely used on many large trucks and on earth-moving plant. Machines like these have one or more engine units delivering anything from 300 to 1,000 horsepower. On our roads, the diesel engine can be a good neighbour or a social outcast. The difference often depends on engine maintenance, for the diesel will keep running despite being badly treated. And even the best maintained engines tend to smell unpleasant and make a lot of noise. If we cannot live without the diesel, how can we make it better company? The heart of the problem lies in the combustion process. Studying this in a variety of operating conditions and analysing the engine exhaust may well lead to ways of reducing harmful emissions and unpleasant smoke. Slow-motion film of the combustion process is also studied, for the rate of mixing of air and fuel as combustion occurs is a crucial factor. Can this mixing be accelerated? And how will this affect nitrogen oxide levels in the exhaust, which may already be rather high? What will happen to the fuel economy? The answer may well lie in the use of other types of combustion chamber, where fuel-air mixing is much faster and combustion is therefore cleaner. Combustion is also the initial source of much of the engine noise, although this is transmitted and amplified by the rest of the engine. In this acoustically dead test cell, ways of reducing noise levels can be evaluated. Special cladding is attached to various parts of the engine in turn, so that the worst noise-emitting areas can be identified. The noise levels at different frequencies can be seen from the analyzer, and the tracing provides a permanent record for comparison. While cladding is quite effective, the only really satisfactory method in practice is the almost complete enclosure of the engine. In this new city bus, the engine has been boxed in and the engine compartment lined with mineral wool matting. The cooling air intake is also designed to absorb the noise produced by the fan and the engine. The result is a passing noise level of about 76 decibels. The previous version of the bus was some 12 decibels noisier at 88 decibels, which to the human ear means that the new engine makes only a third as much noise as the old one. And so the new bus goes into service, a quiet indication that the diesel's problems can be resolved. With locomotives hauling 400 tons or more, we move into a power range where the gasoline engine can no longer compete. Here, the main rival to the diesel is electric power. In fact, most railway diesels generate power for electric motors which drive the wheels. These diesels are much larger and so run rather more slowly, between 800 and 1600 revolutions per minute. Many of them work on a two-stroke cycle. The valves in the cylinder head are for exhaust gases only. On the latter part of the power stroke, these valves open, and then the piston uncovers inlet ports cut into the cylinder wall. Turbocharged fresh air is blown through, chasing out or scavenging the exhaust gases. Then, as compression starts, the piston covers the ports and the exhaust valves close. Locomotive engines of this kind can deliver up to 4,000 horsepower. Medium-speed diesels are also used for electric power generation elsewhere, normally working at slightly slower speeds. At airports, hospitals, and other places where loss of electricity could prove fatal, the diesel is on permanent standby. starting up automatically if the normal supply should fail. In ships of all sizes, there's a growing use of the medium-speed engine as a source of propulsion. The compact size of the engines makes them particularly suitable for car and rail ferries, for instance. This ferry has one flat, straight-through deck for cars, a lower one for trucks and railway carriages, and beneath that, the two V10 engines. Medium-speed marine engines operate on a four-stroke cycle, and at the lower end of the speed range. These two run at 450 revolutions per minute, producing 12,000 horsepower. For other types of cargo ship, the need for maximum possible cargo space is combined with the demand for reasonably good speed. Sailing between Europe and Australia, this ship also uses the roll-on, roll-off principle and has an extremely flexible cargo handling system. It carries its own diesel forklifts and towing trucks. The ship is powered by three 18-cylinder V engines, two side by side, one further aft. And although size is still important, the space restrictions are less severe than for road and rail operation. So the power developed per cylinder can be greatly improved. And the latest engines of this type now produce more than 1,000 horsepower per cylinder. Engines running in this part of the medium speed range call for the use of gearing, so that a suitable propeller speed can be used. In this case, all three engines are geared to a single shaft and propeller. One other variation of the medium-speed diesel is a two-stroke engine with opposed pistons. Running at 300 revolutions per minute, it produces 2,500 horsepower per cylinder. The opposed piston engine has two pistons sharing the same cylinder. As they approach each other, the air between them is compressed, fuel is injected, and combustion occurs, forcing the pistons apart again. The upper piston uncovers the exhaust ports, while a moment afterwards, the lower piston reveals the inlet ports, allowing fresh air to be blown through and scavenge the remaining exhaust gases. Power from the top piston is transmitted by two side connecting rods to crosshead couplings. From there, it passes on via two more rods to the crankshaft. The lower piston has a single center connection. And so, as the medium-speed engines continue their development, they will certainly prove more of a force in the future. But in the meantime, how do we drive this? For bulk carriers of 100,000 tons or more, the answer lies either with the steam turbine or with the slow-speed diesel. These mammoths run at 100 revolutions per minute or less. Burning lower quality residual fuels, they are the most efficient of all diesels, developing up to 4,000 horsepower per cylinder. They all use a two-stroke cycle, and various methods of scavenging are employed. Used here, and probably the most effective, is the Uniflow system, which we saw earlier on the railway diesel. Air is blown in through inlet ports at the bottom of the cylinder, and forces the exhaust gases out through a single valve in the cylinder head. An alternative which dispenses with the valve and allows simpler cylinder construction is cross-flow scavenging. The exhaust gases are expelled through ports set on the opposite side of the cylinder to the inlet ports. In loop scavenging, however, inlet and exhaust ports are on the same side of the cylinder. The sheer size of these engines means that the piston and cylinder wall must be lubricated separately from the crankshaft. The lubricant itself must combat the corrosive effects of burning low-quality fuels. An important consideration in all engines is freedom from vibration. The crankshaft especially must be perfectly balanced. In design and production, absolute precision must be achieved, and that's not easy, working on a scale like this. Even so, machining must be accurate to within 1/100th of a millimeter. Engines like this can deliver 40,000 horsepower. And though they're probably reaching their limit in terms of size, their design is continually being improved. This new version on trial here has several innovations, notably the use of hydraulic valves instead of the old pushrod and rocker arm. The diesel engine is the workhorse of the modern world, perhaps the most remarkable engine of any we have. In the 80 years of its history, it has become indispensable in every sphere of transport, industry, and agriculture. In all its great variety of applications, the future of the diesel engine seems almost unlimited.